Today we're going to be doing an electromagnetic radiation experiment with a laser pointer, and I'm going to be tying it in a little bit with the graph I have up behind me that you might be familiar with. Here I have a laser pointer, and it's shining down onto a sheet of aluminum foil with 3 pinholes that I poked through. Each pinhole is a different size. It can be tough to make out, but there's several thick rings that you can see. You can see about into the 3rd ring. I can maybe see 4. I don't know. But they're pretty thick, and this is the smallest pinhole. This is the 2nd pinhole. It's a little bit larger than the first one, and we can see that we have a little bit more diffraction lines from the laser pointer shining through, and they're a little bit thinner. Here we have the very last pinhole. It's the largest. We can see that there's even thinner diffraction lines, and there's even more. In conclusion, we can note that with a smaller hole size, we'll have a smaller number of diffraction lines. And as we increase the hole size, the number of diffraction lines will increase. This will continue to happen until the diffraction lines disappear because the light will shine straight through. We can also make a note that as the number of diffraction lines increase, the size of the diffraction lines decreases. The graph that we're going to be taking a closer look at is made up of the elements of the periodic table. It's not just the elements though, it's the elements and their different stable isotopes. The elements that we know of from the periodic table can actually exist in different states of having more neutrons in their nucleus, as they're called. And the more neutrons in there will change the weight of the isotope, and it can become radioactive or it's stable. And as we see here, I have the 2 stable hydrogen atoms, hydrogen 1 and hydrogen 2, and I have 3 of the stable neon atoms, neon 20, 21, and neon 22. Looking at some more isotopes, we have hydrogen, helium, and neon with 2, 2, and 3, argon, krypton, and xenon, which are heavier elements, and they can have 3, 5, and 8. So as we increase the number of neutrons and nuclei inside of the nucleus, we can eventually increase the number of stable isotopes that we actually have, as seen here with xenon, that has 8 stable isotopes. Now, this is similar to the diffraction line experiment that we just did, because as we actually increased the size of the hole, there was more possible diffraction lines. More diffraction lines were basically shining through the hole. And so we kind of see electromagnetism showing up in the stable isotopes. It does take other funny patterns and turns, but we're going to take another closer look at the decrease in size of these diffraction lines to show that I mean business what I'm talking about, possibly. Now, in order to get the values that I used to plot on the graph, I simply take the number of protons divided by the total mass of the stable isotope. And this would actually be a part divided by the whole, which gives us a decimal, which we can then multiply by 100 to make it a percentage number. Which we don't even have to do that, it'll just be a decimal at some point, whatever, percentages are decimals. So 1 divided by 2, which would be, there's 1 proton making up the stable isotope hydrogen, and 2 of the weight basically equals 50%. And so on and so forth. And I then plotted these values onto the graph as I have a graph here displaying the isotopes we just talked about. I have the percentage values here for where these isotopes will end up based on their number of protons to the number of the actual weight of the element. And so you have hydrogen here, which has 2 stable isotopes and a range of about 100% proton to 50% proton to neutron mass. I'm trying to get rid of the neutron idea here, so that's why I was going at this concept. And here you have helium, has a smaller range. It's about 65%, we could say, to 50%, so it's got about a 15% range. And they both have the same amount of isotopes, stable ones that is. And now with neon and argon, they both have 3 stable isotopes, but their range is actually shrunk to about 5% range for where they actually exist on these proton to nuclei ratios. And then 5 here and 8 here with about a 2% or 3% range. It's starting to get pretty crazy because as we're shrinking the percent range for where these elements will actually exist in their stable states, the number of them is actually increasing. And so it's really crazy because it's as if the charges themselves, as they're flowing around each other or around the atoms, making the atoms, they're following this sort of weird structure that they just hold to, and it's like everything we're looking through is just a pinhole shining through or a light shining through a pinhole, kind of. It's pretty strange. So, and last but not least, the graph itself. You can see it in its entirety. The thick black lines, or the blue lines, are the elements that don't actually have any stable isotopes, and they'll radioactively decay into other elements. So they don't technically exist, I guess. But you can see hydrogen and helium. And going on down, if you see a single line there, basically means that there's only one stable isotope. And so there's just this funny dance that the elements are doing, and they eventually increase in size. There is one element that I can't remember, but it has 10 stable isotopes. And you can see where I stop referencing that there was no more stable isotopes. Pretty neat.